Thank you. Can you hear me clearly?
Yes.
Okay, good. Okay. Um, Morning, everyone. Thank you for coming. First of all, let me present my special thanks to the organizers of this conference. I'm sorry I cannot go to the conference physically because we are still in the COVID pandemic in China. Okay, so today I'd like to give some review talk about some progress in this area. This talk is partially based on my collaboration work with Renzo and my friend Xin Li. So the talk is divided into 4 parts. Firstly, the motivation. Then I will review 3 important tools in this direction, crossing numbers or row plans to be exact. Then HOMFLYPT polynomial values. And the last one is topological complexity degree as geodesic distance. Okay, motivation. This is the scheme of this motivation, and I will give you details below. Let's start from laboratory and numerical experiments in classical and quantum fluids. This page, the stuff come from the work of William Irvine's group in Chicago. In classical and quantum fluids. In both the two contexts, you can see the decay from a state of high complexity to a low complexity. Another example is this, from here to here, and here, and then here, right? So they are from complicated state to a simple one. The same story happens in biology, in DNA biology. So this page comes from the work of Mario Vasquez's group in UC Davis. In 2013, they gave us an optimal route of decay from torus link to trivial link, right? Then in 2017, they gave us a more detailed diagram showing the different routes from one state to another state, from here to here. And we can see there are so many midway stages in between the initial point and the final point. There are totally 9 routes for T26. This one is T26, the torus link, from that one to decay to here. And the old one, or the 2013 one, this guy, is just the route here, which possesses the largest probability of occurrence. So we can see the same phenomenon happened in 2 different disciplines, fluid mechanics and DNA biology. So we have the following observation. A knot-plex system usually is highly unstable. It intends to experience a free degeneration. So that one is a free degeneration from a high complexity state to a low one through a series of midway stages. Every stage is a knot or link. So from one stage to another, there is a topological transition. For example, it could be a reconnection event. And within the event, there is a certain amount of energy loss. So we have the following picture in our mind. Fluid vortex tangles with different topology form a discrete hierarchy of structural complexity. And every level corresponds to a certain energy level. So maybe, I just say maybe, we can use topological complexity hierarchy to define an energy hierarchy or to produce a one-to-one correspondence between the two, between this hierarchy, to that spectrum. We can use that one to use the former to manage the latter. So this just ask us to recall the proposal of Arnold. Arnold once gave us some proposal that maybe it's possible to find some algebraic invariants whose mathematical hierarchy could be used to manage the hierarchy of physical states. So that means, in the language of dynamic systems, that means there exist some dynamic flows in algebraic space. So how to do this job? Our dream is to find a scalar to quantify the complexity degree. Why scalar? Because in physics, energy is a scalar. So if we can find a scalar as to play the role of complexity degree, then it will be convenient for us to establish a direct one-to-one correspondence from topology to energy. So below, in the following 3 parts, I will review 3 scalar tools. The first one is crossing numbers. Second one is HOMFLYPT polynomial values. The third one is geodesic distance in algebraic space, spanned by some Legendre polynomial basis. Okay, tool 1, crossing number, or rope length to be exact. We will see a logarithmic law for ground state energy versus not linked numbers. This work is based on 2 papers by Renzo and Francesca Maggioni. Okay, let's start from the magnetic knot setting up. So this is a magnetic knot with center line as a knot and some cross section S, and the total length is L and the volume is V. Magnetic flux is defined as this, and the magnetic energy is this. So this page is setting up. We focus on the tight configurations of the knots and the links. That means if initially we have such a knot, we ask it to go to relax, and then finally arrive at this tight configuration. Then we focus on this one and that one, right? We compute the energy of this guy and this guy. So the progress in this area is the following. In 1990, Keith Moffat just gave a bound for m min, just this, where this small m is a function of the internal twist. Then in 2008, Renzo Rica just gave a further explanation for m. It is a function of not only h, but also k. K is a knot type. He focused on the 0 framing condition case, h equal to 0 case. Then this m is this, in proportional to C min. C min is a crossing number. But this result is still a loose result, because within the category of even each given C min, there still exists a number of distinct knot types. So we must find some refined structure for m min. So he goes on, he went on, and then have the following discoveries. In this paper, Francesca and Renzo just give us this result. Then introducing the concept rope length lambda. Lambda is what? Is a ratio between L star and R star. L is a total length of the knot, and R star is the radius of the cross section, right? So we just ask this one to be the characteristic quantity. It is computed that M main could be expressed by lambda and h in this way. This one, pretty good. This term contains h, this term lambda, right? Then, furthermore, if we focus on the h equal to 0, the zero framing case, then we have this. This is a lambda to the 4/3 law, right? Very nice. The energy is proportional to lambda. Lambda is a topological quantity. Below, I have my own understanding of this law. I'm not sure if Renzo agrees to this one. How to understand this law, this power, especially this power. Let L to have a expansion to PL. Then the cross section will be 1 over PS. Then the magnetic field will be P this. Then energy will be P squared. At the same time, R goes to 1 over this square root of this, then lambda will go to this. We compare this multiple and this multiple, we can see that one is this one's power to this, implying this law. This is my own understanding. Then based on that, one can compute the energy M and use the length, the rope length to sort the knots. Then we have the sorting number, this one. Then we obtain such one. The logarithmic law for tight knots, prime knots, and prime links. So this is a kind of logarithmic law. The best fit curves are the following: this guy and this guy. All right, so this is a 2-1. The second tool is HOMFLYPT polynomial values. This work is based on the following two papers in 2015 and 2018. The purpose of writing this paper is to deal with such a degeneration procedure from this torus link T26 to trivial knot. Okay, the story begins from helicity. We know helicity is defined as follows. It is a triple integral, u and velocity and vorticity, the dot product in between, right? In 1969, Kismovat, and in 1992, Renzo Ricca and Kismovat give us the following formula. The left-hand side is helicity, which is a triple integral, but the right-hand side is simple algebraic numbers, self-linking number and the linking numbers. So the triple integral is turned into simple algebraic counting of numbers, right? So this formula is so important, so useful. However, there are still some weakness within this formula because linking numbers sometimes fail to detect essential topology. For example, self-linking number 0 cannot tell this circle and this fig 8 knot. And the linking number 0 cannot tell this fig and this Brownian rings and what hat link. So in 2012 and 2015, Renzo and myself wrote two papers giving two theorems about constructing knot polynomials in terms of helicity. in this GFM paper, we just give a theorem saying that the power, this exponential form for helicity satisfies the scaling relations of HOMFLYPT polynomial. So that means we can construct a HOMFLYPT polynomial in terms of helicity, where the helicity is written in the line integral form. Okay. In this talk, I ignored the proof of this theorem because it is not the main topic of the talk. Then, based on that, we can input some physical information into the polynomial. In the polynomial, for example, for HOMFLYPT, we have this. Trifle knot, we have this. The polynomial contains two parameters, A and Z. We ask Z to represent the contribution of rise helicity, and A to present the contribution of twistor helicity. Then we can give special evaluations to Z and A. Z, we ask it to be 1.04 and A to be 1.28. Then, naturally, we can compute the values of those HOMFLYPT polynomial. For example, left-handed trifle knots has a value of 2.636. Okay. All right, now we are ready to study the torus links and the torus knots. Here is a series, is a family of torus knot and torus links, right? Then in 2016, we give a formula for the polynomial, for the HOMFLYPT polynomial of torus links and knots. This one, where we can substitute A equal to 1.28 and Z equal to 1.04 into that. Then we have the value of torus knots and links, just like this. We obtain a monotonically decreasing sequence for HOMFLYPT values. It is a monotonically decreasing one. Yeah. So this result is pretty good. Yeah. If we compare the performance of HOMFLYPT, Jones, and Alexander Conway polynomials, we can see HOMFLYPT is the best one. So we have a conclusion. HOMFLYPT values could be a useful scalar tool in detecting torus knot link topology. Furthermore, polynomial environments could play a key role in quantifying topological complexity of knot systems. So far, it's good, but we still have some more dream. For the third tool, I will talk about some new tool, complexity degree of knot links in abstract algebraic space. So this is the scheme. This paper is section is based on our collaboration work published in 2020. Okay, as I mentioned in the motivation section, in laboratory and numerical experiments, in DNA biology and vortex dynamics, different discipline have the same phenomenon in common. But those are just experimental observations, not theoretical study. Yes, there is some theoretical study, but I have to say it is a kind of a semi-theoretical study because they are numerical simulations in DNA biology. This, right? Some numerical simulations. So we need something mathematical, I think. So we need some theoretical study, true theoretical study. Can we use the not polynomial values to do this job? I think the not polynomial values have some disadvantages. The first one is, for example, if we compare the left and the right-handed truffle nodes, in our opinion, we think they should share the same complexity, left and the right-handed one. They should share the same complexity. But if we directly compute the HOMFLYPT polynomials, their values are different. So it is not acceptable. The second weakness is in our last two HOMFLYPT polynomial values, we focused on the torus nodes and the links. They are only a particular family, right? They are only particular family. How about other types of nodes and links? We need to develop some general method to quantify topological complexity degrees, right? So we have the following idea. Geometric flow in a algebraic space. In our mind, the picture is the following. A link in a free circumstance will degenerate from its position towards the space, towards the origin of the space. So that means if we have a abstract algebraic space, then a knot could be represented by a point in the space, right? Then the degeneration procedure just corresponds to the moving from the knot point to the origin of the space. And different physical states are represented by a series of equivalent surfaces labeled by the scalar, right? For example, if the space is flat, then this equivalent surface could be some spherical surfaces, right? Spheres. And a decaying path, which is a degenerating root penetrating equipotential surface. Just as demonstrated in this picture. For example, this one is a knot plot. This is the origin, and all the green lines just indicate the equipotential surfaces. The degeneration procedure from here to here corresponds to a line penetrating those surfaces, right? Then we can see maybe the optimal path is nothing but the shortest route in this picture. So our scheme of research is the following. Technical. So this page just contains some technical details. We consider a space of the Jones polynomial for knots and links. Then a knot is a point in the space. and we let n0 be the origin of the space. And how to obtain the coordinates of this point, of this not point? We use the orthogonal polynomials. For example, we use the Legendre polynomial as a basis to expand the algebraic space. Then every point, every not point could obtain a set of coordinates. That means we can obtain the coordinate through the projection, the John's polynomial of the knot and the Legendre polynomial as a basis, right? Then we obtain a set of coordinates. Of course, we still have to give some extra, additional rules or requirements, restrictions, that we deny the transitions from knot to knot and the transitions from link to link. We only permit the transitions from knot to link or from link to knot. Okay, then in such a picture, optimal route of degeneration corresponds to geodesic in space. So we consider the picture of the UC Davis group. We consider those configurations and compute their coordinates like this. We have the following data for T26, the starting point, the initial point. The coordinates is this. For that one, this, right? Then every point has a coordinate. Then in this page, we can define the complexity degree. Firstly, we define the geodesic distance. That is the distance between the knot point and the origin of the space. We define this guy to be the distance. Then we use a log function to express the complexity degree. Yeah, there are some technical details within that. Yeah. Then using this definition, we can compute the complexity degrees of those knots, 1, 2, 3, 4, 5, 6, those knots. We just see a very fantastic sequence. This is a T26, the initial point. The midway stage, and that one is the final one. We can see a monotonically decreasing sequence, right? And these three guys corresponds to the first row. These three guys form a cluster within the second row, and so on, third row, and so on, right? So this result is pretty good, I think. Then, if we ask a degeneration root has a monotonically decreasing complexity degree. If we put upon this requirement, then we can find 17 roots in total. As I mentioned in UC Davis group paper, they found 9 roots by using their own method. Here, we use our pure mathematical method. We found 17 roots. So I think maybe we have got more roots. If we put upon some biological requirements, the number of 17 could decrease to 9, I think, yeah. That means if we have, if at the beginning we start from many roots, for example, 100 or thousands of roots, we can use mathematical method, our mathematical method, to pick up 17 roots from the hundreds rows, and then we can put some extra biological requirements to reduce the number from 17 to 9. That is possible. And we can also compute the probability of occurrence for those roots. There are 17 roots here. We can compute the probability of occurrence. We can also compute the branching ratio for every site. The black numbers is 3.7% and 4.5%. All those black numbers, they are the original data from UC Davis group, and the red guys, red numbers, are our old data obtained from our mathematical method. So this is a way to define the probability. Okay, I have to emphasize that, I have to stress that this line, which I showed here, this line coming from the definition of complexity degree. It is a kind of logarithmic curve. We can do best fit curve for that. It is this. If we recall Ricca and Maggioni's result in 2014 and 2018, for example, we go back to here. These are their best fit curves. These are our best fit curve. Okay, conclusion. We try to realize Arnold's idea, that is developing appropriate algebraic invariants to label topological complexity of a complex system. Then we can use that, the hierarchy of this complex, of this topological complexity, to manage the physical hierarchy. I mean the energy spectrum. So this is Arnold's idea. So we aim to find topologically invariant scalars to play the role of complexity degrees, such that we can establish a correspondence between topological complexity hierarchy and energy spectrum. We can use the left one to manage the right one. I reviewed 3 tools. The first tool is crossing numbers, rope length to be exact, versus magnetic energy, where we can see topological hierarchy, because rope length has different values for different knot types. And spectrum yes, also has a hierarchy. So we can make correspondence between these two hierarchies. And in 2 and 3, I reviewed HOMFLYPT values and the geodesic distance method. These two methods can also give topological hierarchy. But so far we haven't got the energy spectrum. So I have to say it is still ongoing work. Yeah. Finally, I'd like to give a advertisement for my students' talk. Guan Hao tomorrow afternoon he will give a talk on numerical simulations of degeneration of Borromean rings vortex filaments in superfluidity governed by GPE, Gross-Pitaevsky equation. There he will give us some degeneration map for Borromean rings. The theoretical analysis is nothing but our method of 2, 3. Yes. Okay, this is the references. And thank you so much. Have a good excursion this afternoon.